So welcome back to the second part of this video. So in the first video we introduced linear systems of equations, how to solve them using the graphing method and the substitution method. And those two, I highlighted their sort of pros and cons. Another method is the addition method, and this can be a really clever way of solving problems. It's not always obvious how it, if it'll work, but if you can see a connection between equations, it's a really quick way of solving problems cleanly. So this is the addition method, and let's look at an example here. Two systems of equations. So we've got 3x minus 5y equals negative 9, and 4x plus 5y equals 23. And what we're going to do here is simply add or subtract, as the case may be, the two different equations together. Okay, so if I just stack these like we did before, add like terms only, right? So we want to add numbers together, add y values together, and add x values together. And what we get is we get 7x plus 0y equals 14. So that 0y is where the trick comes in. What you're really looking for is a case where you can completely cancel one of your terms. You want to get rid of one of the variables by doing this. Okay? So in this case, we were very lucky. We had a positive 5y and a negative 5y, and just by adding those, they cancel off. Similarly, if we would have had a positive 5y and a positive 5y, we could have subtracted our two equations to get those to cancel. Okay? So we solve this, and we find that x equals 2, and now all we have to do is plug in this x value and solve for y. Okay, so I'm plugging this into the left-hand equation up here. Combining like terms and solving for y. And we see that our solution to this point is x equals 2, y equals 3. Okay, so this x comma 2 is a solution to both of these equations. Well, let's look at another example. This one's a little bit more tricky. We've got 2x minus 3y equals negative 13, and we've got 5x minus 12y equals negative 46. Okay, so just at first glimpse, none of these terms are going to cancel. Our x nor y value will cancel. But, so we're looking just to cancel one of these values. But what we can do is we can multiply our top equation, this equation up here, by negative 3, or rather by negative 4, in order to make that term a positive 12y. Okay? So as long as we do the same thing on the left-hand side of our equation as we do on the right-hand side of our equation, we're just fine. This is no different than solving an equation where we divide both sides by 3, something like that. Okay? So that's all we're doing. We're just seeing that, look, if we multiply that top equation by negative 4, if I add these two equations together, they'll then cancel my y values. So let's go ahead and look at that. I'm going to go ahead and multiply my top equation by negative 4, which gives me negative 8x plus 12y equals 52. And now I want to add this equation to my second equation. Okay? Adding up like terms, again, stacking it such that I've got numbers, y values, and x values. So my y's cancel out, which is what I was looking for. Similarly, I could cancel my x values. It really doesn't matter. And I find that x equals negative 2. Okay, so now we've got our x equals negative 2 value. We need to plug this back into one of our equations. Doesn't matter which one. So 2 times negative 2 for our x value minus 3y equals negative 13. Combine like terms, solve for y, and we've got y equals 3. Okay? So this is one very clever way. Doesn't always work if you've got, decimal points or things like that, or it's, this won't always work. But if you can see a nice connection, it's a very easy way of solving these problems. you don't end up with more ugly equations, which you could with the substitution method. Okay? All right, so that's another way of solving these problems. Let's look at a more complicated problem. Here we're going to have, I've got multiple variables, but what I actually mean here is we have a system of equations with x, y, and z, and I'm leaving a little, little foretelling here, infinite solutions. So I hinted at this in the last video, but we're going to see it and what it looks like in this type of equation. Okay, so here we've got three systems of equations, each with three variables. Okay, and now just a quick side note. If you ever have a system of variables like this, to get an exact answer like x equals 1, y equals 2, z equals 3, you need at least as many equations as you have variables, okay? So with our previous examples, we only needed 2 equations because we only had 2 variables. Here, we have 3 variables, so we need 3 equations at least. Good. Okay, so here's our 3 equations. So I'm just going to take equation 1 and 2, and what I notice is that if I multiply equation 1 times 3, I'll see that my y values will cancel. Okay, so I've got negative 3 here. If I multiply that times positive 3, I'll get negative 9y, and that'll cancel with this positive 9y. Okay, so I'm going to go ahead and do that. So if I multiply that equation 1 times by 3 on both the left and the right hand side again, and then just add these 2 equations, hopefully you see immediately that what this is going to give us is 0 equals 0, right? By multiplying equation 1 times that 3, all the x, y, and z terms all canceled out. Okay, so this gives us 0 equals 0. But what does this mean? Okay, 0, of course, always equals 0. But that's the point, right? Is that 0 always equals 0. So that tells us that all numbers, any combination of x, y, and z that satisfies this equation, or similarly equation 2, so because they're the same, is a solution to this system of equations. Okay, so this is like looking back at our graphing method. This is when we have basically two parallel lines that completely overlap each other. They're the same equation. Okay, if we multiply them, they look exactly the same. So any number that is a solution to this equation is also a solution to the entire set of linear equations. So this is one way we can write it in sort of set notation here. In jargon, what this means is that we have a system of linearly dependent equations. We don't have to worry about this too much, but you may, if you go on to other things or if you do any computer science kind of stuff, this is sort of a big deal. Linearly dependent basically just means that 2 equations look exactly the same if you multiply them by a single number. So so in this case we multiplied our equation by 3 and we saw that those 2 equations were exactly the same. So those are linearly dependent. What we really want is linearly independent equations. That's when you'll find a solution, a single or at least a couple of solutions to these equations. So we've looked at 3 different methods of solving these equations. All of them have their place. Like I've said, graphing method, that's great when you have a computer that can solve very precise numbers and it can do it very quickly. The substitution method is my sort of go-to, especially if things are fairly neat looking, because I don't always like to, have to pay attention to when some terms are canceled. But sometimes things just add up beautifully and you can use this addition method and it makes your life a lot easier. So they all have their place, but yeah, so you'll figure out which one would work best for you.